Hi students, welcome to Future Doctor NEET Academy for the crash course in NEET Physics. The topic chosen today is Chapter 10, Mechanical Properties of Fluids. Fluid means that is liquid and gases combinedly called as fluids. Pressure, what is pressure? Pressure is nothing but force or thrust acting per unit area is called pressure. SI unit of pressure is Newton per meter square or Pascal. Dimensional formula mL power minus 1 T power minus 2. And this is from Pascal's law, that is a pressure applied to any enclosed fluid is transmitted to all the fluid and the wall of the container equally. And from that only, that is F2 equal to, that is F2 by A2 equal to F1 by A1, that is a formula. So from that F2 equal to A2 by A1, and its application is hydraulic lift, hydraulic press, hydraulic brakes. This is a hydraulic lift. Small force applied here to overcome or lift the big force or big weight as car-like structure. Pressure exerted by liquid column P equal to H rho G. Here H is the depth of liquid, rho density and G acceleration due to gravity. Variation of pressure with depth P equal to PA plus H rho G. Here PA is the atmospheric pressure. And what is atmospheric pressure? It is the pressure exerted by atmosphere is called atmospheric pressure. At sea level, atmospheric pressure equal to 0.76 meter of mercury column. That is, in olden days we used mercury barometer as a measurement or device used to measure atmosphere or pressure. So we compare that with mercury column. Mathematically, 1 atmosphere equal to 1.013 into 10 power 5 Newton per meter square or Pascal. Next term, Archimedes principle. Archimedes principle states that when a body is immersed completely or partly in a fluid, that is in a liquid, water-like liquid, it loses in weight equal to weight of the fluid displaced by it. Mathematically, apparent weight equal to true weight minus V rho G. Actually, this is M into G formula. This is nothing but mg, and we know what is the relation between density and mass. Density equal to mass by volume. Okay, from this mass equal to density into volume, that only mg becomes rho Vg, that only. Okay, and V is the volume of the fluid displaced and rho is its density. And this is the diagram for buoyant force or upthrust. Mass of the object, weight of the object. Mass is maybe in kilogram, which is constant. Weight is due to gravitational force. Mass is not changing, but weight will be changing because of upthrust or buoyant force. And loss of flotation and all derived from here only. Next, viscosity. What is viscosity? It is a property of liquid due to which a backward dragging force acts tangentially between two layers of a liquid when there is relative motion between them. Newton's formula for viscous force. The viscous force between two liquid layers, each of area and having a velocity gradient dV by dx is F equal to eta A into dV by dx. Here eta is called coefficient of viscosity, and coefficient of viscosity is defined as the tangential viscous force which maintains unit velocity gradient between two parallel layers each of unit area. That is viscosity, coefficient of viscosity eta equal to force acting per unit area maintained at unit velocity gradient. This is the formula for viscosity. And unit also we have discussed. Unit is n m power minus 2 into s. Is it so? Ns m power minus 2. M power minus 2. And n m power minus 2 we can write as Pascal. Pascal into second. That only this. Poisson equation. When a liquid of coefficient of viscosity flows through a tube of length L and radius r, the volume of a liquid flowing out per second is given by V equal to pi p r power 4 into 8 eta L. Here P is the difference of pressure between the two ends of the tube. And Stokes law. Stokes law, there is a backward dragging force acting on a small sphere of radius r falling with uniform velocity v through a medium of coefficient of viscosity is F equal to 6 pi eta r v. Eta r v or eta a v. R or a is the radius. And terminal velocity is the maximum constant velocity acquired by the body while falling freely in a viscous medium. And the terminal velocity v of a spherical body of radius r and density sigma while falling freely in a viscous medium of viscosity eta, then density is given by v equal to 2 by 9 r square by eta into sigma minus rho into g. Here v is the terminal velocity. By knowing the terminal velocity, we can determine the coefficient of viscosity of a liquid eta also. Streamline. Streamline is a path straight or curved, the tangent at any point to which give the direction of the flow of liquid at that point. Tube of flow is a bundle of streamlines having the same velocity of fluid elements over any cross section perpendicular to the direction of flow. Streamline flow is the flow of liquid in which each molecule of the liquid passing through a point travels along the same path and with the same velocity as the preceding molecule passing to the same point. This one. Here both the preceding point and succeeding point will be same velocity. That is a streamline. Laminar flow is the flow of liquid in which velocity of layer varies from maximum at the axis to the minimum for the layer in contact with the wall of the tube. That is called laminar flow. And flow is basically two types, streamline flow, another one turbulent flow. It is the flow of liquid in which a liquid moves with a velocity greater than its critical velocity. The motion of particles of liquid becomes disorderly or irregular. And this is for streamline flow, and this is a turbulent flow. Its velocity will be different at each point. And critical velocity is the velocity of liquid flow up to which the flow of liquid is streamlined and above which its flow becomes turbulent. That is a critical velocity in which turbulent flow can be converted into streamlined flow or streamlined flow can be converted into turbulent flow. Formula Vc equal to K into eta by rho into r. Here rho is the density of liquid flowing through a tube of radius r and eta is the coefficient of viscosity of liquid. And Reynolds number only decides the whether the flow is a streamlined flow or turbulent flow. It is a pure number determines the nature of flow. Formula for Reynolds number is n equal to rho d Vc by eta. Rho is the density, d is the diameter of the tube, Vc critical velocity, eta coefficient of viscosity. And if the Reynolds number value is less than 2000, then we can say the flow is streamlined flow. And if it is greater than 3000, it is called turbulent flow. And if it is in between 2000 to 3000, uncertain flow. That is, it can switch from streamline to turbulent or turbulent to streamline. We have to start from here, no? Okay. Theorem of continuity. If there is no source or sink of the fluid along the length of pipe, the mass of the fluid crossing any section of the pipe per second is always constant. That is A1 V1 rho 1 equal to A2 V2 rho 2. This is called equation of continuity. For incompressible liquid means rho 1 equal to rho 2. Density will be same. Then the equation of continuity is A1 V1 equal to A2 V2. A1 is the area of cross section of the pipe or radius of the pipe like that, and V1 is the velocity. And diagram back is okay. And Bernoulli's theorem, it states that for an incompressible non-viscous liquid in steady state, the total energy, that is pressure energy, potential energy and kinetic energy, remains constant. That is called Bernoulli's theorem. Pressure energy is P by rho, and potential energy, actually all are energy per unit mass. That is a potential energy formula we know, mgh. mgh by m, that is gh. Okay, and pressure energy is actually PV. Okay, and PV by m, volume by mass. That is a density equal to mass by volume, then volume equal to mass by density. So that only given. Okay, so as P by rho. And same way of mv square, kinetic energy of mv square per unit mass, m is getting cancelled, so of v square constant. So P by rho plus gh plus of v square is constant, or P by rho g, that is a divided by g in all the, divided by g throughout. Then P by rho g, gg cancel, h plus v square by 2g. Okay, so this is the another form of Bernoulli's theorem. Next topic, surface tension. Surface tension is a property of a liquid by virtue of which it behaves like an elastic stretched membrane with a tendency to contract so as to occupy a minimum surface area. Surface tension is a property of a liquid by virtue of which it behaves like an elastic stretched membrane. That is, surface of the liquid acts as a stretched membrane with a tendency to contract so as to occupy a minimum surface area. That is, it tries to reduce the surface area, minimize the surface area. That is called surface tension. Mathematically, surface tension equal to force per unit length. Okay, force per unit length. And SI unit is Newton per meter. Dimensional formula for force is m L T power minus 2 by length L. L getting cancelled, therefore m L power 0 T power minus 2. Surface energy. Surface energy is a potential energy per unit area of the surface film is called surface energy. It is a potential energy per unit area of the surface of the film is called surface energy. Surface energy equal to work done in increasing the surface area by increasing area. That is the surface energy. Work done in increasing the surface area by increasing area. And surface tension is numerically equal to surface energy. So surface tension is equal to surface energy. Numerically equal to surface energy. Noted? And this only on the surface. See, inside a surface, this drop or this molecule having force in acting in all the direction. But on the surface, how is that? Force is acting only inside, bottom, and upward there is no force. That is why surfaces tries to reduce the area minimum. That is why surfaces acts as a stretched membrane. Okay, that is called surface tension. And excess of pressure inside a drop and bubble. And one more thing here, this one. This angle of contact we are going to study for this. This is a liquid drop. How is that theta value, that and all we will discuss. There is an excess of pressure on concave side of a curved surface. Excess of pressure inside a liquid drop equal to 2T by R. 2T by R, and T is the surface tension, R is the radius. And excess of pressure inside a liquid bubble equal to 4T by R. This is another formula we will do in problems. Okay, that is a pressure inside a liquid drop 2T by R. For a liquid bubble 4T by R. And excess of pressure inside an air bubble, this is for liquid bubble. For air bubble means 2T by R. Here T is a surface tension, R is the radius of the liquid drop. And this R is the radius of liquid bubble. And angle of contact. Angle of contact is the angle which the tangent to the free surface of the liquid at the point of contact makes with the wall of the containing vessel is called angle of contact. The angle which the tangent to the free surface of the liquid at the point of contact makes with the wall of the containing vessel is called the angle of contact. See this one, this theta is only angle of contact. Okay, and that may be acute or obtuse. That we will see. For liquid having convex meniscus, the angle of contact is obtuse, and for having concave meniscus, angle of contact is acute. That in next picture will show. See, this is one, this is a convex and this is a concave meniscus. Okay, that is, what is this? Actually, this is a capillary tube. This is capillary tube, and if you insert a capillary tube, if you dip capillary tube inside a water, beaker containing water, what will happen? It's like this. And same capillary tube, if you insert inside a mercury, it will be like this. What's the difference between these two? Here, this is actually, this is the level of water. What about the level of water? Increases. That we are calling capillary rise. Capillary rise. And suppose for mercury, what will happen? What will happen? Its height increase or decreased? That is, we are calling this as a, it's not a capillary rise, it's a capillary fall. Capillary fall. Okay. And this only we said. Angle of contact is obtuse for convex meniscus, and for having concave meniscus it is acute. And capillary tube. A tube of very fine bore is called capillary tube. Okay, capillary tube is tube of, it's made up of glass only, having very fine bore. That picture I will show. And capillarity, rise or fall of a liquid inside a capillary tube when it is dipped in it is called capillarity. That is, for water, rise takes place. For mercury, capillary fall takes place. And this is called capillary rise or capillary fall is called capillarity. Okay, this only I said, for water capillary rise, for mercury capillary fall. And here concave meniscus, and this is a convex meniscus. And this is cohesive force. So actually, what is cohesive force means? Cohesive force is a force between the same substance. Same substance. For example, water with water. Here one picture, no? This is a cohesive force. That is a force between the water we can call cohesive force. And adhesive force. What is adhesive force? Different substance. Best example is Fevicol. In Fevicol we may observe it is a good adhesive. Adhesive means Fevicol attracts or stick another substance. So this is the adhesive force. Adhesive force means different substance. Force between different substance. That is Fevicol where we are using, carpenter and all using, no, that is in carpentry. So Fevicol tries to stick the wood-like articles. So that is different adhesive. And angle of contact, if theta equal to 0, strength of cohesive force weak, adhesive force is strong. And degree of wetting, perfect wetting. And meniscus is plane, no concave, no convex. We show no concave, convex. This is a concave and this will be convex meniscus. And this will be plane meniscus. So there is no rise or no fall. And if theta is less than 90, theta is less than 90 means it's acute or obtuse? Acute. That is acute. If it is acute, cohesive force is weak and adhesive force strong. And degree of wetting also high and meniscus will be concave. Concave meniscus where we have seen water. Capillary tube when it is dipped with water. Rise of liquid, liquid will be water here. And if theta is greater than 90, what is that? Obtuse, no? Is it so? Obtuse. Cohesive force strong, adhesive force weak, degree of wetting low. Your degree of wetting high. That's why, that is if you touch water or water with glass, we may observe after pouring the water outside, if you touch the surface of the beaker, we may feel wetting. Is it so? Some drop will be sticking on that. But same way mercury, if mercury is poured inside a beaker and mercury pour out and if you touch, there is no wetting, that only low wetting. And meniscus will be convex meniscus. Rise of, fall in the capillary, fall of liquid. Here what substance I said? Mercury. Mercury is an example for capillary fall or convex meniscus. Angle of contact is obtuse. This only here we said. Here angle of contact is acute and here obtuse. Convex meniscus, concave meniscus. Capillary rise, capillary fall. And see, water on silver surface is a plane, theta equal to 0. Water on the silver surface. There is no meniscus, plane surface, plane meniscus. And glass plate on water. How is that? It will be what kind of meniscus? Convex or concave? This is a convex meniscus. And theta will be acute or obtuse? Acute. Convex and theta is acute angle, that is less than 90. And for glass on mercury, it will be obtuse and concave meniscus and theta is obtuse. Okay. That is why because of this theta value as greater than 90, mercury does not stick in a glass or mercury not wet the glass. Not only glass, even our hand also. I don't know whether you use mercury or not. By touching, it will go spreading like that. Okay, it will not stick. And formula for capillarity. H is a capillary height, H equal to 2T cos R by rho or G. And from this, we can determine the surface tension of a liquid or water. T equal to H rho or G by 2 cos theta. And for this only apparatus setup is, this is apparatus, I will show it. This is only apparatus setup for that. Okay, there is a beaker containing water and capillary tube is just dip inside. It will be raised to a certain level. That water level will be raised to a certain level. This is a capillary rise. Best example for capillary rise is that is wick in a stove, tiri. Okay, actually that thing we are inside the oil in lamp and all. In lamp and all, that wick will be there and oil will be, that is till oil will be used up. It will be glow continuously. How means that's due to surface tension or capillary rise only. And this is actually capillary tube inside, inner radius of the inner diameter of the capillary tube. Capillary tube is like this, cross-sectional area of a capillary tube. Note down this form. So T equal to H rho Rg by 2 cos theta. H is the height of the capillary rise. Accurately we can measure using traveling microscope or vernier microscope, and rho is the density of a liquid. Water will be used. Density of water will be 1000 kilogram per meter cube, or radius of the capillary tube. That also using traveling microscope we can find. G acceleration due to gravity 9.8. Theta is the angle of contact. For water, theta will be in problems and all, theta value will be given. For water, this value will be acute, less than 90 degree. And there will be rise in the liquid when angle of contact is acute, and obtuse when angle of contact is obtuse. Okay. And this is the equation of continuity diagram, that is A1 V1 equal to A2 V2, or AV is constant. And actually AV is constant, which means that the volume flux or flow rate remains constant throughout the pipe, or the smaller the cross section, greater will be velocity. If cross section is small, your area of cross section is small, A2, area of cross section is small, then velocity will be greater. So V2 is greater than V1. V2 is greater than V1. What about A1, A2? A1 is greater or A2 is greater? Area of cross section. A1 is greater than A2. So A is inversely proportional to V, or AV equal to constant. That AV equal to constant only, A1 V1 equal to A2 V2. Okay. And Bernoulli's theorem, that also we have discussed. According to Bernoulli's theorem, sum of the pressure energy, kinetic energy and potential energy per unit mass is constant. This is for incompressible non-viscous fluid in a streamline flow. P by rho plus V square by 2 plus GH equal to constant. Okay. Next chapter, thermal properties of matter. Thermal properties of matter. What is thermal meaning? What is thermal? Yes, thermal means heat. Temperature and heat. Temperature is a relative measure of hotness or coldness of the body. Simply definition for temperature is this one only. Temperature is the degree of hotness or coldness, or measure of hotness or coldness of a body. That is called temperature. SI unit of temperature is Kelvin. And commonly used unit, other units are degree Celsius or degree Fahrenheit. Degree Celsius or degree Fahrenheit. And conversion from Kelvin to Celsius, T Kelvin equal to T degree Celsius plus 273.15. Suppose there is a value 0 degree Celsius, example. Zero degree Celsius, convert into Kelvin. Then T in Kelvin equal to T in degree Celsius, that is 0 plus 273. So T in Kelvin equal to how much? 273 Kelvin. So like that we can convert degree Celsius to Kelvin, just adding 273. Heat. What is heat? Heat is a form of energy flow between two bodies or between a body and its surrounding by virtue of temperature difference. If there is a temperature difference, then only heat will flow. SI unit of heat is joule. Commonly used unit, calorie. 1 calorie equal to 4.186 or 4.2 joules. Approximately we can give 4.2 joules. That is, this is 1 calorie. SI unit of SI unit of heat is joules only, but in nutrition there and all we may use calorie. For example, this food gives this much amount of calorie, like that only we are using. So that is a conventional unit of energy. Heat always flows from a higher temperature system to a lower temperature system. Measurement of temperature. Observation of thermometric property with change in temperature and comparing it with certain reference situation. That is, reference situation is generally ice point and stream point. Okay, for example, for in Celsius scale, ice point, that is freezing point. Ice point or freezing point is the temperature at which liquid converted to solid. That is only ice point or freeze point. For water, 0 degrees Celsius is the ice point. And for stream, 100 degrees, not 1000, 100 degrees Celsius is the for stream 100 degrees Celsius. 100 degrees Celsius is the stream point or boiling point. In Fahrenheit scale, ice point will be 32 degree F, 32 degree Fahrenheit, and stream point will be 212 degree Fahrenheit. From this it implies that 100 division in Celsius scale is equal to 180 division in Fahrenheit scale. 100 division in Celsius scale equal to 180 division in Fahrenheit scale. Then T minus 32. That is, suppose in Fahrenheit scale means TF minus 32 equal to TC minus 0. TC, actually TC minus 0, TC minus 0, TC, that's why it's given like this. TF minus 32 by 180 equal to TC minus 0 by 100. How is it 180 coming? Means 212 minus 32, that only 180. This 180 is 212 minus 32. Difference between stream point and ice point, that is equal to 180. That only this 180. Similarly, 100 minus 0, that is 100. Okay. So by having this idea, we can convert any unit of scale to other unit of scale, as Fahrenheit to Celsius or Celsius to Fahrenheit or Fahrenheit to Kelvin, like that. In Kelvin scale, ice point is 273.15 Kelvin. Stream point 373.15 Kelvin. Then comparing this with the Kelvin scale, degrees Celsius with the Kelvin scale. T minus 0 degrees Celsius by 100 equal to T minus 273.15 by 100. T minus 0 is just T. So, T in degrees Celsius divided by 100 equal to Tk minus 273.15 by 100. This 100 getting cancelled. Then T in degrees Celsius equal to T in Kelvin minus 273. So this is to convert Kelvin to Celsius or Celsius to Kelvin. Already we studied, that is a T in Kelvin equal to how much? T in degrees Celsius plus 273. Okay, so Kelvin to Celsius means minus 273 and Celsius to Kelvin plus 273. And Kelvin scale is called absolute scale and temperature is called absolute temperature. In many definitions we may study is the absolute temperature or absolute scale. What is that absolute temperature means? Kelvin scale is the absolute temperature. And Kelvin scale is the absolute scale because it is practically impossible to go beyond 0 Kelvin or in the negative Kelvin. No negative Kelvin. 0 Kelvin itself extremely very high cold, high chillness. Beyond or less than 0 Kelvin, so far not achieved. Okay. So that's why we are calling Kelvin scale is the absolute scale or absolute temperature, because 0 Kelvin is the minimum least. Okay. And this is a comparison of 3 scale: Kelvin scale, Celsius scale, Fahrenheit scale. See a steam point 373.15, 100 degrees Celsius, 212. Ice point for Celsius 0 degrees Celsius, for Kelvin 273.15, and for Fahrenheit 0. For Fahrenheit 32, no? Yes, 32. That is 32 degree F. And absolute 0, 0 Kelvin, minus 273, here minus 273. It's a comparison of Kelvin scale with Celsius scale and Fahrenheit scale. And thermal expansion. Next topic, thermal expansion. It is widely observed that most of the material expand on heating and contract on cooling. All the material, all the metal or all the substance, when temperature increases, it will be expand, and temperature decreases, contract. This expansion will take place in all the dimension. And experimentally it has been observed that fractional change in any dimension is proportional to the change in temperature. Fractional change in any dimension proportional to change in temperature. That is the normal expansion. And there are different types of expansion. Suppose expansion takes place only along length, then that is called linear expansion. This is linear expansion. See, this is a one rod, okay, having L length, and when temperature increases, it will be increases like this, slightly as dl or delta L. Now we can say this is a linear expansion. This is the L is the length of the material and delta L is the increase in length. Then fractional change in length, delta L by L, actually delta L by L is proportional to delta T, increase in temperature. Okay, delta L by L is proportional to delta T, and by removing proportionality we are giving a constant, that constant only alpha. What is alpha? Alpha is called coefficient of linear expansion. Alpha is called coefficient of linear expansion. Similarly, area expansion. Suppose expansion takes place in 2 dimensions as length breadth, we can say that is area. Then fractional change in area, delta A by A, is proportional to delta T. And as usual, by removing proportionality we are giving a constant, that constant is beta. Beta is called coefficient of area expansion. Okay. And increase in area per unit area per degree rise in temperature, that is called coefficient of area expansion. And next is volume expansion. Suppose there is a fractional change in volume is proportional to delta T, then here proportionality constant is gamma, and here gamma is called coefficient of volume expansion. And here this linear expansion is a one-dimensional expansion, and area expansion two-dimensional expansion, and volume expansion three-dimensional expansion. Okay. Heat and calorimetry. When two systems at different temperatures are connected together, then heat flows from higher temperature to lower temperature till the time their temperatures do not become same. Two systems at different temperature connected together, then heat flows from higher temperature to lower temperature. That already we know. It will flow from higher temperature to lower temperature till the temperature do not become same. Till the temperature same, it will transfer will takes place. And principle of calorimetry states that neglecting heat loss to surrounding, heat lost by a body at higher temperature is equal to heat gained by the cold body at lower temperature. Heat gained equal to heat lost. This is principle of calorimetry. Heat loss equal to heat gain. And whenever heat is given to any body, either its temperature changes or state changes. Temperature changes means increase in temperature. State change means solid state to liquid state or liquid state to gaseous state. That is a state change. Based on this only, latent heat of fusion or latent heat of vaporization all will come. And change in temperature, when the temperature changes on heating, then heat supplied is proportional to change in temperature delta T. And heat supplied is proportional to amount of substance. Heat supplied is proportional to nature of substance. And delta H equal to or delta Q equal to MS into delta T. Note down this formula. Both the formula will be used for principle of calorimetry problems. Delta H or delta Q or delta Q equal to M into S into delta T. Delta T is a change in temperature and S is the specific heat capacity. S is the specific capacity and M is the mass of the body. Specific capacity formula, that is the unit is joule per kilogram per Kelvin. This is the formula for specific heat capacity. And delta H equal to N into C into delta T. This is another formula. If instead of M mass, if you use N as a number of moles, instead of mass M, if you use N as number of moles, then N into C into delta T. C is called molar heat capacity. C is called molar heat capacity. Suppose the mass, instead of mass, if you are measuring in number of moles, then specific capacity is changed as molar heat capacity or specific molar heat capacity. Specific heat capacity is the amount of heat required to rise the temperature of unit mass of the substance through 1 Kelvin. This is the definition for specific heat capacity. What is specific capacity? Is the amount of heat required to rise the temperature of unit mass of the substance through 1 degree or 1 Kelvin. And unit joule per kilogram per Kelvin. And specific capacity of water 1 calorie per gram per degree Celsius. That is commonly used value will be calorie per gram into degree Celsius. And specific capacity of water at ice point equal to 0.5 calorie per gram per degree Celsius. This is in gram. Value 1 means that mass is measured in gram and energy is measured in calorie and temperature is measured in Celsius, degree Celsius. Okay. Molar heat capacity is the amount of heat required to rise the temperature of unit mole of a substance through 1 degree unit or 1 Kelvin. SI unit joule per mole into Kelvin. What is molar heat capacity? Amount of heat required to rise the temperature of unit mole of the substance or 1 mole of the substance through 1 degree Kelvin or simply 1 Kelvin. SI unit joule per mole into Kelvin. Common unit calorie per gram into degree Celsius. And heat capacity. Heat capacity is the amount of heat required to rise the temperature of system through 1 Kelvin. This is only heat capacity. S is the heat capacity or specific heat capacity. And delta H is the heat energy raised or lower. Delta H equal to S into delta T. And its unit is joule per Kelvin. Heat capacity unit is joule per Kelvin. Specific heat capacity joule per kilogram per Kelvin, and heat capacity just joule per Kelvin. Common unit calorie per degree Celsius. For water with specific capacity does not change but fairly very less. Water is having less specific heat capacity. And material with higher specific heat capacity require a lot of heat for some given in temperature. Change in state. When the phase changes on heating, then heat supplied is proportional to amount of substance which changes the state. Heat supplied is proportional to amount of substance which changes the state. That is, delta H is proportional to amount of substance which changes the state, is proportional to M. Delta H is proportional to M. And it also depends on nature of substance. And here del H equal to M into L. Your L is called latent heat of processes. That may be latent heat of fusion or latent heat of vaporization. And its SI unit is joule per kilogram. Amount of heat required per mass to change the state of any substance. That is called latent heat. Okay, at that time what will happen is temperature maintained constant and there will be a heat energy continuously supplied to the substance. Change in state always occurs at a constant temperature. Change in state always occurs at a constant temperature. For example, solid gives liquid. That is latent heat of fusion. And liquid gives gas. That is a latent heat of vaporization. Latent heat of fusion and latent heat of vaporization. Some important terms. Change of state from liquid to vapor is called vaporization. Liquid to vapor or water into gas or steam. Temperature at which the liquid and the vapor states of the substance coexist is called its boiling point. Temperature at which the liquid and the vapor states of the substance coexist. That is called boiling point. Boiling point of water is how much? Boiling point of water is 100 degrees Celsius. Okay. And boiling point of substance at standard atmospheric pressure is called normal boiling point. And change from solid state to vapor state without passing through the liquid is called sublimation. And the substance is said to be sublime. Can you say any one example for sublimation?
Camphor.
Yes, camphor. Camphor, naphthalene balls. That is and all. Best example for solid state to vapor state without becoming liquid. Heat transfer. There are three modes of heat transfer. There are three modes of heat transfer. One is conduction, another one convection, third one radiation. See, three modes of heat transfer as given in this diagram. By keeping a rod heated at this point, okay, and this point, this end we feel hot. It means heat energy will be transferred through one atom to other atom as a vibration, neighboring a molecule or neighboring atom. So this is the best example for conduction. Convection, what is convection? Convection is a process in which molecule itself transfer. So here what will happen means hot molecule, hot air molecule will rise up and cold air molecule will sinks down. Like that takes place, that is called convection. That is hot air molecule will weigh less and rises up. Cold air molecule will be sinks down. And that's why in refrigerator or even in AC, split AC and all especially, AC and all kept at the top or bottom? Top. That is top. Why? What's the reason? Means that is a air cooler or air condition. It will supply chillness or cool air molecules. Okay. Then what will happen means air molecules, cold air molecules will be heavy, sinks down inside a room. In room inside it will be sinks down. And hot air molecule will be rises up. That is why even exhaust fan, in kitchen and all exhaust fan we are keeping. Exhaust fan where we are keeping, top or bottom? Top. Reason, hot air molecule rises up and it will sucks the air molecule, hot air molecule. Okay, that is the same reason. And actually even air condition, that also it will give cold air molecule and then it sucks the hot air molecule. That is a cold air molecule and all will sinks down and hot air molecule rise up. And another best example in refrigerator. Freezer is kept at the top or bottom? Top of the refrigerator. Okay. And freezer will be closed and inside a freezer temperature will be in 0 degrees Celsius or less than 0 degree. Then only freezing point 0 degrees Celsius. Okay. And from freezer only all the chillness will be coming down. So hot air molecule and all sinks down and then rise up and cold air molecule and all sinks down inside. And here this is a convection. Convection means here hot air molecule rises up and cold air molecule falls down. So like that we are receiving heat energy by convection. Radiation. Without any material medium we can receive the radiation, that is the radiation. Conduction. Thermal conduction is the process in which thermal energy is transferred from the hotter part of the body to the colder part, from hot body to a cold body in contact with it without any transference of material. That is the conduction. Note on this formula for conduction. Rate of heat energy transferred flowing through the rod becomes constant. Q is equal to K into A into Tc minus Td by L. Tc minus Td by L. That is how it is derived means Q is directly proportional to difference in temperature. Okay, this difference temperature Td Tc. You are comparing Tc and Td, Tc will be greater. So Tc minus Td and inversely proportional, and also Q is proportional to area of cross section, and Q is proportional to 1 by L, thickness. Okay. And by combining all the things, Q is proportional to A, Tc by Td by L you will get. And by removing proportionality, we will get a constant, that constant is K. And K is called thermal conductivity or coefficient of thermal conductivity. That is called K. What is K? K is called coefficient of thermal conductivity. Note this formula, no? And see, Q is the rate of heat energy flow, A area of cross section, Tc, Td are the temperature at hot and cold end, and L is the length of the rod, K is the coefficient of thermal conductivity. Its definition is defined as the amount of heat conducted during steady state in unit time through unit area of any cross section of the substance under unit temperature gradient. That is called coefficient of thermal conductivity. Its unit watt, m power minus 1, k power minus 1. This is the SI unit, not this one. J by m, no, that is not a SI unit. Only watt, m power minus 1, k power minus 1 is the SI unit of thermal conductivity. Next, temperature gradient. Fall in temperature per unit length in the direction of flow of heat energy is called temperature gradient. Temperature gradient will be denoted by symbol dt by dx. Even yesterday we discussed velocity gradient dv by dx. Same like that. And term Q and its unit. Unit of temperature is Kelvin, distance meter, so Kelvin by meter. And term Q is the rate of flow of heat energy and also we named as heat current. And term LKA is called as thermal resistance of any conducting rod. Thermal resistance is the obstruction offered to the flow of heat current by the medium, and its unit is K by W. There is thermal conductivity by thermal resistance. Next topic, convection. Convection is in which heat is transferred from one point to another point by the actual movement of the heated material particle from a place at higher temperature to another place at lower temperature is called thermal convection. I said no, hot air molecule rises up, cold water molecule sinks down inside. So it means actual molecule transfer takes place, movement takes place, that is convection. Even water, another best example is boiling of water. And if you boil water here, then first we may observe that that is a bottom having the molecules, water molecule, absorb the heat energy and rises up. Okay, and cold air molecule will be sinks down inside. If the medium is forced to move with the help of a fan or a pump, it is called forced convection. Example of forced convection: circulatory system, cooling system of an automobile, heat connector. These are examples for forced convection. Cooling system, air cooler or air conditioning system is the best example. Radiation. Third mode of heat transfer is radiation. Radiation is a process of transmission of heat in which heat travels directly from one place to another without the agency of any intervening medium. There is no material medium is necessary to transfer. That is the radiation. Best example for radiation is solar radiation or sun radiation. We receive solar radiation even in vacuum. We can transfer solar energy and we will receive solar energy by the process called radiation. The radiation of heat energy occurs in the form of electromagnetic waves. That only we said. Electromagnetic wave, what is the name of the radiation? IR. What is IR? Infrared. Already I said infrared light or infrared wave having one peculiar property, it produces heating effect. IR is a heating effect. These radiators are emitted by virtue of its temperature, like radiation by a red hot iron or light from a filament lamp. Every body radiates energy as well as absorbs energy from surrounding. And the proportion of energy absorbed depends upon the color of the body. Dark color or black body, black color, absorb more amount of energy. This radiation, this only we discussed. Next, Newton's law of cooling. In this also we will do some problems. Newton's law of cooling states that the rate of loss of heat d by dt minus d by dt of the body is directly proportional to the difference of temperature difference. Minus ds by dt equal to k into T2 minus T1. Here k is a positive constant depending upon area and nature of the surface of the body. Suppose a body of mass m, specific capacity S is at temperature T2 and T1 be the temperature of surrounding. If D2 is the solid temperature, then we will work out some problem. ds by dt or dq by dt or ds by dt in terms of fixed value, you can determine k value. Here k is a positive constant depending upon area and nature of surface of the body. Suppose a body of mass m, specific capacity S is a temperature T2 and T1 be the temperature of surrounding, then if D2, the fall of temperature in time dt will be observed. Next, Stephen's laws of radiation. This formula also you can note down. That is, rate at which energy transfer or energy radiated per unit area per unit time is directly proportional to the fourth power of absolute temperature. Okay, the rate at which energy radiated per unit area per unit time is directly proportional to the fourth power of absolute temperature. By removing proportionality, we are introducing a constant. That constant is sigma. E equal to sigma T power 4. And sigma is a constant value 5.678 into 10 power minus 8 watt m power minus 2 k power minus 4. Sigma is a value, given value, constant value. Wien's displacement law, that is, wavelength corresponding to maximum energy is inversely proportional to its absolute temperature. Lambda m is inversely proportional to T, or lambda m is proportional to 1 by T. Then lambda into T equal to B. That is lambda m is inversely proportional to T, then lambda m into T equal to B. B is a constant called Wien's constant. This is called Wien's constant. B is called Wien's constant value 2.89 into 10 power minus 3 m into Kelvin. Using this also we will do lot of problems. And temperature depends upon the color, that also discussed in these problems. Next to chapter 12th. Thermodynamics. What is thermodynamics? It's a branch of physics that deals with the heat with mechanical work or heat with mechanical energy. Conversion of heat energy with mechanical energy or relationship between heat energy and mechanical energy. That is the thermodynamics. Okay. And thermal equilibrium. Before thermodynamics, we want to learn some terms. Thermal equilibrium. If two systems are said to be in thermal equilibrium with each other, if they have same temperature. Two systems are said to be in thermal equilibrium with each other if they have same temperature. Then only we can say that is thermal equilibrium. And thermodynamical system. It is an assembly of large number of particles having same temperature, pressure, etc. is called thermodynamical system. And thermodynamic variables. The variables which determine the thermodynamic behavior of a system are called thermodynamic variable. Example, pressure, volume, temperature. These are the thermodynamic variables. Zeroth law of thermodynamics. Zeroth law of thermodynamics states that if two systems A and B are in thermal equilibrium with the third system C, then the two systems A and B are also in thermal equilibrium with each other. If two systems A and B are in thermal equilibrium with the third system, thermal equilibrium means same temperature. Suppose A and B are in same temperature with C, then A and B is also having same temperature. That is the indirect meaning. So instead of same temperature, we are saying equilibrium, thermal equilibrium. If A and B are in thermal equilibrium with a third system C, then two systems A and B are also in thermal equilibrium with each other. And thermodynamic process. Thermodynamic process is said to be taking place if the thermodynamic variable of the system change with time. That is pressure, volume or temperature, anything will be changes with time. That only thermodynamic process. Based on that only we will say isothermal process, adiabatic process, isochoric process, like that. Okay. Yes, isothermal process. Note down this one, because in this lot of problems, lot of definition things will be asked. Iso means same, thermal means heat or temperature. So process taking place at same temperature or constant temperature, that is the isothermal process. Process taking place at constant temperature or same temperature. And adiabatic process. Process takes place in which there is no exchange of heat. No exchange of heat energy takes place, that is the adiabatic process. And isochoric. Isochoric means it's a process taking place at constant volume. Volume is constant or same volume. That is isochoric. Isobaric means process taking place at constant pressure. Pressure is maintained constant. Cyclic process. Process where the system returns to its original state. For example, initially it is on one state, one pressure with one volume. And when temperature increases, it will go, changes. And again, when we reduce the temperature, if it comes back to same position, same P1 and B1, then we can say that is a cyclic process. And equation of state. A relation between pressure, volume and temperature for a system is called equation of state. What is equation of state? It is a relation between pressure, volume and temperature. PV equal to constant or PV by T. PV into T, like there is some relationship. And indicator diagram. PV diagram or indicator diagram, the graphical representation of a state of a system with the help of two thermodynamical variables is called indicator diagram. That is a pressure with volume, change in pressure with volume. That only we are calling indicator diagram. It's a graphical representation with the help of two thermodynamical variables as pressure with volume, change in pressure with change in volume. First law of thermodynamics. First law of thermodynamics states that amount of heat dq is added to a system, a part of heat is used in increasing its internal energy, while the remaining part of heat may be used up as the external work done by the system. That is, amount of heat energy added to a system, then some amount of heat energy is used to increase the internal energy. Increase the internal energy means the temperature may change, increases, and remaining part is used for external work. Okay, that is the first law of thermodynamics. What is that first law? That is, heat energy given to the system, then entire heat energy is not converted to work. Some amount of heat energy is used to increase the internal energy of the system. That increase the internal energy of system only may be increase in temperature. Then dq is the energy given to the system, and du is the internal energy of the system, increase in the internal energy, and dw is the work done. Work done. Then dq equal to du plus p into dv. Actually, w equal to pv is the formula. W equal to p into v, and dw means one thing will be constant, and here p will be constant, there will be a variable is v, as v1 to v2 or v2 to v1, like that. That only. dq equal to du plus p into dv. Here what is dq? dq is heat energy supplied or given to the system, and dw or pdv is the work done by the system or given to the system by the system, and du is the change in internal energy of the system. Internal energy changing means temperature will be increasing. And work done during expansion or compression of a gas. When the volume of a gas changes from V1 to V2, work done is given by W equal to integral V1 to V2 P dV. Work done formula W equal to integral V1 to V2 P dV, and there may be a closed integral. W equal to integral V1 to V2 P dV equal to area under the PV diagram. This is equal to area under the PV diagram. Okay. And isothermal process. Isothermal process is a thermodynamic process that takes place at constant temperature, and that is called isothermal process. And equation of state, we said no, what is equation of state? Which gives a relation between P, V, T and all. So equation of state for isothermal process, PV equal to constant. P into V equal to constant. It means when pressure increases, volume decreases. P is inversely proportional to V. P is inversely proportional to V. When P increase, V decrease. And work done during an isothermal process, that is W iso equal to RT into log of V2 by V1, or log base E, that is equal to 2.303 into RT into log of V2 by V1. This is not E, here there will be a 10. Here will be, this will be 10. That is log base E to 10 only, this is a formula. Okay. Log to the base E equal to 2.303 into log of 10. But nowadays calculator we are using, so no need to convert this one, but in olden days we know only log table. Okay. So in log table, log to the base 10 only will be there. Then natural logarithm, that is a log to the base E. There will be a need of conversion of natural logarithm to log to the base 10. So this is the conversion, 2.303 into log of some log x to the base 10. Okay, that is natural logarithm log to the base E. Mostly we will use as natural logarithm of x equal to 2.303 into log of x base 10. Okay, log x to the base 10. Then adiabatic process, thermodynamical process that takes place in such a manner that no heat enters or leaves the system. That is called adiabatic process. This is called adiabatic process. And equation of state for adiabatic process, PV power gamma equal to constant. And another formula, T into V power gamma minus 1 constant. Other formula, totally 3. P into gamma minus 1 by T power gamma equal to constant. In these 3, any one will be used for adiabatic process. First one, PV power gamma equal to constant. Second one, T into V power gamma minus 1 equal to constant. And third one is P into P power gamma minus 1 by T power gamma equal to constant. And work done during adiabatic change, W adiabatic equal to R into T1 minus T2 by gamma minus 1. R into T1 minus T2 by gamma minus 1. This is work done during adiabatic process. And note down this one, that is del Q is positive, that is heat energy. Del Q is the heat energy. When it is positive means when heat is supplied to a system. So based on the value, problems, the theoretic problems will be asked when heat energy is supplied to a system. Del Q will be positive or negative. And work done by the gas, positive or negative. Work done on the gas, like that. And here del Q is positive when heat is supplied to a system. And del Q, that is heat energy, is negative when heat is drawn from the system. Okay, when heat is drawn from the system, del Q value negative. Del W, what is del W? Work. When work done is positive, when work done by the gas, at that time expansion takes place. Work done by the gas, expansion takes place. And del W, that is equal to negative when work done on the gas, that is compression. Compression, okay. And delta U, internal energy, is positive when temperature increases, internal energy increases. Delta U positive means temperature increases and therefore internal energy also increases. And delta U is negative when temperature decreases, internal energy decreases. So based on this, that first law of thermodynamics, no, what is the formula for first law of thermodynamics? Yes, dq or del q. As per this formula, delta q equal to delta u plus delta w. Like that problem will be discussed in there based on the heat energy supplied or drawn or work done by the gas or work done on the gas. This may be positive or negative. Based on that, we are going to work out some problems later. And reversible process is a process in which the system can be retraced to its original state by reversing the conditions. That is a reversible process. What is reversible process? It is a process in which a system can be retraced to its original state by reversing the condition. And irreversible process is a process in which a system cannot be retraced to its original state by reversing the condition. That is an irreversible process. Next, second law of thermodynamics. Second law of thermodynamics states that it has two statements, Kelvin statement and Clausius statement. Kelvin statement and Clausius statement. Kelvin statement, it is impossible to derive a continuous supply of work by cooling a body to a temperature lower than that of its surrounding, lower than the coldest of its surrounding. This is a Kelvin statement. It is impossible to derive a continuous supply of work by cooling a body to a temperature lower than that of the coldest of its surrounding. This is a Kelvin statement. Best example, refrigerator or even AC. That is a, forget AC, refrigerator. Refrigerator, inside a refrigerator, temperature inside a refrigerator is greater than or less than room temperature, surrounding temperature. In a refrigerator, inside a refrigerator, the temperature inside a refrigerator is greater or less than the surrounding, that is a room.
Greater.
Actually, what is the temperature inside the refrigerator? In freezer, 0 degrees Celsius. Apart from freezer, other area and all, how much it will be? It may be in 5 degrees Celsius or 10 degrees Celsius, like that, is it so? Less than room temperature. So, temperature inside a refrigerator is less than the surrounding temperature or our room temperature. Okay. And but what's doing? By switching on, compressor motor is working and continuously it's supplying the some amount of energy such that it reduces the temperature continuously. And see what is the, now see that it is impossible to derive a continuous supply of work by cooling a body to a temperature lower than that of surrounding without any external work. Actually in there we are doing some external work, motor work is there, motor compressing motor work is there such that it can transfer heat energy from a refrigerator inside a refrigerator to a outside. And if you go back side of the refrigerator, you may feel hot. Is it so? It means it will continuously transfer heat energy from the inside a refrigerator to the outside. Okay. And by itself, is it possible? Means not possible. That is only Kelvin statement. Actual Kelvin statement is it is impossible to derive a continuous supply of work by cooling a body to a temperature which is inside a refrigerator lower than that of the surrounding, that is surrounding temperature. But it is possible only when some work is initially we are doing some external work. By itself it is not possible. Okay, next Clausius statement. It is impossible for a self-acting machine unaided by any external agency to transfer heat from a body to another body at higher temperature. That is a refrigerator inside temperature will be lower temperature and room temperature outside will be higher temperature. And what is happening? Continuously supply heat energy from inside a refrigerator to outside the refrigerator. That is some external work is done. And without any external work, that's not possible. That is only Clausius statement. It is impossible for a self-acting machine unaided by any external agency. Unaided means without any external agency to transfer heat from a body to another body at higher temperature. That is the Clausius statement. Next, heat engine. Heat engine is a device for converting heat energy into mechanical work. Heat energy into mechanical work, that is a heat engine. And petrol engine also is a one type of heat engine only. Petrol or diesel, it will be combustion takes place and converted to heat energy, and that heat energy is converted into mechanical work by piston like engine. Component of heat engine, source of heat, and source is the region having infinite amount of temperature, that is the T1 temperature. T1 is the temperature of the source and Q1 is the energy of the source and T2 is the temperature of the sink and Q2 is the energy at the sink. working substance. Working substance is a gas or fuel. Okay. For our petrol engine, petrol, liquid, and after combustion it converts into gas. And efficiency of heat engine. Efficiency defined as the ratio of the external work obtained to the amount of heat energy absorbed from the source. It is defined as the ratio of the external work obtained to the amount of heat energy absorbed from the heat source. So, work done by heat energy absorbed. Simply efficiency is nothing but efficiency eta equal to work by heat, W by Q, that is Q1. We may ask Q1 or Q2, that is Q1. And this W is nothing but that is only Q1 minus Q2 by Q1, that only this formula. Okay, Q1 minus Q2 by Q1. And if you split this one, Q1 by Q1 minus Q2 by Q1. Then what is happening? Q1 cancel, that only 1. 1 minus Q2 by Q1. Okay. So, W equal to Q1 minus Q2, that is work done. W equal to work done Q1 minus Q2, and Q1 is the heat energy of the source of heat. That is equal to 1 minus Q2 by Q1. This is the efficiency of the heat engine, and efficiency will be always greater than, no, less than 1. And Carnot heat engine. Carnot's heat engine is an ideal heat engine which is based on Carnot's reversible cycle. And the efficiency of Carnot heat engine is 1 minus Q2 by Q1 equal to 1 minus T2 by T1. That is, that is Q1 is proportional to T1 and Q2 is proportional to T2. Then Q2 by Q1 equal to means T2 by T1. Therefore, eta equal to 1 minus Q2 by Q1 equal to 1 minus T2 by T1. 1 minus T2 by T1. And refrigerator heat pump. It is a heat engine working in backward, reverse way. And here we are saying efficiency, no. Just like efficiency for refrigerator, coefficient of performance, that is denoted by symbol beta. Beta is the coefficient of performance. And it is equal to Q2 by W. Heat absorbed from cold body by W. Heat absorbed by cold body by W, and Q2 by W is Q1 minus Q2. Q1 minus Q2, and that is equal to T2 by T1 minus T2. Q2 is T2 and Q1 and Q2 is T1 minus T2. So, beta equal to T2 by T1 minus T2. This is the coefficient of performance. And for heat engine means efficiency is important, and for refrigerator means coefficient of performance is important. Eta value and beta value decides the efficiency of the engine, that performance. Okay. Okay. Thank you, students. Thank you. And in next session, we will follow remaining units. That is chapter 12, 13, 12, 13, 13, 14. Yes, 13, 14 and 15. Okay. Okay, thank you all.